All right. Woohoo! There you go. Good afternoon. How's everyone doing? Woohoo! All right. I took a mini nap because it's Saturday and it's very warm, and I just felt like doing it. So I'm a little fussy right now. Um, just get myself some coffee, decaf, of course, and where was I going? What were we doing this afternoon? Hello, what's up? What were we doing this afternoon? Oh, we were exploring what could we do with the data sets that we discussed this morning. Interesting. Okay, so hi Kiran, Pavel, how you doing? Okay, so good afternoon, everyone. We're back. So, what we're doing this afternoon, for those of you who might be new, this morning we recorded a bunch of videos where we broke down the basics of how to. Where am I? We broke down the basics of how to take a CSV file, parse it, and then use that data to represent it in 3D. We were using Rhino and Grasshopper to do that, and then we were able to take these data sets of pre-recorded motion with game controllers from an HTC Vive headset, and then we were able to use that to generate these things, to generate this where am I? To generate these collections of planes in three-dimensional space that represent the motion of the gamer that was taking these controllers and was moving them in three-dimensional space. Okay, so we did that this morning. So we wrote like all the CSV parsing in C#, etc., and I pointed to where users can download this data set. I may actually just do it again here on the repository of the course that I teach at Harvard. On assignment 0, there's a zip file. Let me actually download. There's a zip file that with all those recordings, and I'm going to download it because I'm going to use it right now. And then what we're going to do this afternoon is that I'm going to record an algorithmic modeling challenge, and that's going to be now taking this data, and with all the data already parsed and all the planes and all the information, then let's see what can we do with it. Let's see what kind of visualization of this motion in three-dimensional space can we recreate. So as opposed to other algorithmic modeling challenges, what this one is going to be a bit more exploratory. So there's not a clear goal. It's going to be more about let's try things out and let's see what we can do about it. Let's try it out on different recording and then let's see what we like and how we can visualize it in interesting ways. So yeah, and for those of you who might be new, I wanna remind everyone about the Discord that we have offline. This is the Discord channel that we have for offline conversations, and yes, and with that, I think what I'm going to do is before we start, when I finished the exercise this morning, I didn't really fully read all the information that is available on the dataset. I didn't fully read everything. I didn't read the trigger value. I didn't read the touch keys, and I didn't read this either. So I think I'm going to use like a few minutes to write all that code for both controllers, and then I will start from there. I also probably want to write myself a list of the things that I want to try in the algorithmic modeling challenge. So I may actually want to invite people in the chat to give suggestions. So again, remember, we have a data set in a CSV file. We have already parsed the data. So we have all this data in a component. I'm going to finish doing that right away. And then what we have is basically two collections of planes, one for each hand of the user, and then how they move in three-dimensional space. Okay, and then So what I would like to offer here in the chat is like to ask for suggestions about, okay, we have two collections of planes. What can we do? What kind of geometry can we generate on top of these planes to visualize this motion in three-dimensional space? Okay, I have some ideas of things that I want to do, but if you want to give me some suggestions, I'll be happy to implement those as part of the algorithmic modeling that we're going to do. So let me, before we go on any further, let me finish writing the CSV parser that we were working with, the list of data. So okay, so I'm going to, first of all, I'm going to take list of timestamps. So that was that was the first column here in the data set. So that's going to be var timestamps. It's going to be a new list of long objects, and this is not long Nguyen. This is a long integer. That was a terrible joke. Long would not be happy about that. Okay. So let me just timestamps. Let me just add convert to long. Don't we have to int 64? That's typical. That's row data 6. Okay, and then that should work. No. Timestamp. Oh, sorry. There's a typo here. Timestamps cannot convert type long to system collections. Oh, because I have to add to the list. Timestamps dot add convert this thing. You see, I still haven't drank my coffee, so I'm like okay. So and here I probably want to add a timestamps, and then here I want to timestamps is equal to timestamps. I'm just finishing what I started this morning, so it's going to take me like 5 minutes or so. I'm letting everyone in the chat think about what can we use to visualize here, visualize this motion. Okay, what kind of geometry, what kind of techniques? Just give it some thought. Okay, and outputs is going to go here. And then what else are we going to do? Var controller 0. What is this going to? Trigger value. That's going to be trigger value is going to be equal to a new list of double elements. And then what else do we have on the list? We have touchpad pressed, touchpad clicked. So that's going to be, I'm going to copy these two here, and then this is going to be touchpad press, touchpad clicked, and then var controller 0, touchpad, and what is this called? So value of x and value of y. So I'm going to use a vector for that. Touchpad values, and that's going to be a new list of vector 3D objects. I'm just using a vector just because it's a structure that I want to use to represent two numbers together in x and y direction. So that's why it's a bit easier to do it that way, I find. So this, now I'm just going to copy paste it here, and list of controller 1 info data, and then here same thing, here 1, 1, 1, and 1. And now very simply we have the controller blah 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 the plane. We have the triggers, this is 10 and 11, and then I probably want to use x equals, I'm going to convert these two values, and this is going to be 12 and 13, and then controller 0 trigger values, add a new vector 3D with x and y and 0. Is this going to work? No, it gives me an error. Controller trigger values does not exist. What? Because it's just one value. Oh, wait. So this is just it's just one number for the okay. Right. Okay. So you see, this is what happens when you do when you rush things out. Value is going to be just convert to Boolean, and then the value of convert to double the value of row data in position 12. And then what do we have? We have here, we have touchpad pressed, touchpad clicked. Here triggers, touchpad, and then we have contour touchpad, touchpad press, touchpad click. So that's going to be 13, 14, and then here is going to be 15 and 16. Trigger and touchpad, this is going to be touchpad values. Okay, is this working? Oh, it is. It is working. That's kind of surprising. And very soon, okay, so now 16 and this starts to 17, so that matches real well. And now I'm just going to copy paste this everything here, and I'm just going to change the numbers here. And so this is going to be number 1, number 1, number 1, and now I have to change the rows. So this is going to be 28, 28, 29, 30, 31, 32, and it still works. Okay, so now I'm going to add the collection. So that's going to be T0 trigger value, and then T0 touchpad pressed. Now it's going to be touchpad clicked, and now it's going to be touchpad values. Okay, and I should do the same also for the triggers. So that's going to be I want to copy this, and this is going to be trigger value, and then touchpad pressed, right? So that's going to be T1 touchpad pressed. Okay, and then touchpad clicked and touchpad values. Is that correct? Okay. Okay, so I'm almost there. So now the only thing I need to do is I need to make sure that all these lists that I just created here have an output going on. So T0 trigger value equals something, which is going to be controller 0 trigger value, and now this is going to be touchpad pressed. It's going to be controller touchpad pressed, and then this is going to be touchpad clicked. There's got to be a better way to do this. This is just so much copy pasting. And touchpad values. Yep. Some T0 trigger value does not exist in the current context. 168. T0 trigger value. So it didn't pick up this thing? Okay, let's see. So trigger press, trigger click, T0 trigger value. And is it not working? Hey Fernando, good afternoon. Trigger value. Okay, so now it's working. There was a typo of some kind. And now this is just to be replaced with T1, 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 and controller 1, controller 1, controller 1. Is that so? So I got a list of falses and trues, values, touchpad values, press, clicked. How is those values 0? Oh, because I'm monitoring. Okay, let me close. I think if we do this one, we should get. Oh, why? No, I don't want to save it. Nope, don't save. Okay. And now for this, I should be getting touchpad values, right? Okay. And then this was not. Okay. All right, that's fine. So, number, timestamps, and then trigger value, so also a number, and then a boolean, and then vector. Okay. And then here, I'm just going to copy paste all of this. And then I'm just going to just put this here for the second controller and all the information that is coming from the second controller. Okay. Is that true? No. This is true and this is correct. Okay. So I think with this we should be ready to start. This is one group. This is another group. Okay. Okay. Alrighty. Okay, so I'm totally zoned out. Alright, so we were saying today, what were we doing? We were now taking this, we were taking this visualization, we were taking these files. So now that we'd had the CSV files, so the motion controller, for example, now that we had the motion, and we had all of this visualized, we had all of this imported into CSV and turned into actual values, I wanted to do something where I wanted to do an exploration of the data and then find a way to visualize this in a cool way. So Kieran is suggesting some kind of abstract visualization using distance and time to graph the accelerated motion and perhaps adding torque also to layer on it eventually. Oh, that's a lot of stuff, but I like where this is going. Okay, I think for starters, I think what I would like to do is I would like to start with just one of these things. So one of the controllers. So let me write myself a few notes here. Motion visualization. Let's start with one controller and place simple geometry on it. Like let's place a cube, let's place a box, let's place a cone. Like do simple stuff. Then after we do that, then perhaps place simple geometry as well with some kind of variation over it. So for example, like maybe we design a box or a line, and then that line grows as we move over. That line grows as we move over the controller. So it starts small and then it grows larger and larger. Or over it, so grows larger, or maybe it has some kind of it has a sine function, so it grows like up and down, up and down. That could be interesting. That could be interesting, and we could use lines for that, for example. Then I would like to create I would like to do something where we place geometry only on the objects that place geometry only if touchpad was pressed. That could be interesting as well. So that we can visualize when the user was pressing the buttons. Now, I would like to also create geometry across the planes. So, create geometry across the planes. So, for example, a polyline across those planes, an interpolated curve. For example, that could be interesting. An interpolated curve. So that could be also interesting. And then I would also like to create geometry that responds to, for example, the speed, to the speed of the motion. Okay, so that would be interesting. So like this length could be somehow a factor of how fast the motion is going. And for this one, perhaps this visualization is not, this file is not great. This one could be a bit better, I think. Because this one changes, this one is very slow here, but it's much faster here, I think. Yep, I think that could work. And then I would like to create, and then I would like to do something with joining the two controller planes. And I think what would be interesting is, like, as I'm doing the examples, I could generate like different C# components. Each one of them doing something different, right? That could be interesting as well. Okay, so are we ready to start then? Is that what I hear? I don't really hear anything. But yes, that's what I think you guys are telling me. So I'm going to take this one. It looks a little cooler. Okay. I'm going to start with simple. So I'm going to record the video in multiple parts. And then by the end, I will record the introduction and see a bunch of, and see like the different possibilities that we, and show like the different things that we created for this video. Okay, so let's do it. Thank you, Kieran. Hoo-hoo. Okay. Let's start. Okay. Wonderful. Let's start. So when it comes to design exploration, what I typically like to do is like, I like to start in simple. Well, first of all, I like doing hand-drawn sketches. I like taking my notebook and like thinking like, oh, what this could look like, and doing some sketches. So so I very much encourage. I don't know what kind of person are you, very digital, very analog, but analog sketching and drawing and drafting things on paper actually works really well for me when I start thinking about these things. So let's imagine we had done a series of like drawing stuff, blah, 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 whatever, and we're ready to start coding. Okay. Something that I like to do, especially when I'm exploring a new environment, and if you are new to Rhino, Grasshopper, and C#, is to start simple, start step by step, and then go incrementally in levels of complexity. So that's why I'm going to start very simple. And the first thing that I'm going to do is I'm just going to use these planes to place very simple geometry on top of them. I'm going to place spheres, cones, cubes, and see what that looks like. And also, for the sake of simplicity, I'm going to start working just with the data for one single controller, for the first one of them. Okay, so I'm going to disable from the visualization the data of the second controller, which is all the data, all the planes, the truths and forces for the buttons, etc., etc. And I'm going to just work with the plane. Okay, so I'm going to create a new C# script component, and what I'm going to do is this is going to be I'm going to call this the plane. All right, I'm going to remove the other input, and then I'm going to plug in here the list of planes that I have imported in my CSV file. Okay, I'm going to right click here and make sure that the type hint is of the type plane, so that when I write code inside of the component, it's a plane object. And then for this one, because I'm just going to be placing simple geometry on each plane, I can keep the access of the item, I can keep it to item, because I'm only going to be working with one plane at a time. So I don't really need to have the list of planes. I'm just going to be using one plane at a time. So for example, something that I can do is I can say, let's say that I'm going to use this component to just place simple geometry on top of these planes. Okay, so what I can do is, for example, I can say, let me create a sphere S by saying, let me create a new sphere object, and then as I open parentheses, it's asking me, okay, what do you want to do here? Do you want to use a center and a radius, or do you want to use a plane and a radius? Well, I do have the plane already, so that is the plane that is coming from the input, but I'm missing the radius. So for the time being, let me just hard code something. Okay, so I'm going to do 0.01, and then I'm going to spit out that sphere on the output S. As I do that, then what I can probably see is that now I have all this collection. Let me turn this off. I have this collection of spheres floating in space, and which are centered right at where each one of the planes is. So this looks pretty cool. It looks like some like, I don't know, like Cinderella when the fairy, I don't know if it was the fairy, like her godmom, I don't know who she was, like the this woman that showed up and did like salakadula chachikumula, boom, the pumpkin is now a card. Okay, I think that was pretty cool. Anyway, but this is very simple. Okay, so let's focus on, we probably want to have control over what we're doing, right? So I'm going to enhance this component by saying, let me add another parameter input, which I'm going to call value. And I'm saying value, I suppose, well, let me say radius. Okay, let's start with radius. And then let me do a double value here. And then what I would like to do is I would like to place here a slider, for example, from 0 to 1. Remember, these planes are very small. And then I would like to use this value as the radius of my spheres. But you can see that I'm plugging this and I'm changing it, and nothing is really changing. Okay, nothing is changing because I haven't linked that new input with the value that I'm using for the spheres. So if I now replace this hard-coded value with the input radius, then you can see that now the spheres will have that input value that from my component. And you can see that everything is going a little slow because actually rendering whatever this is, 200 spheres, 300 spheres, is actually quite computationally intensive for the renderer. So you can see how this is many objects. Should I find a file that has less data? Maybe I can find that in the next post that I do. But for example, I can now click here and say this should be 0.03. And then it's going to take a few seconds to compute because, again, rendering curved geometry is actually fairly expensive in Rhino, and there's a lot of spheres. But you can see that I now have this here in my 3D view. Okay, so just for the sake of cleanness, let me here just write sphere, okay, as the output. And then here in my console, inside of the script, I'm just going to say the output sphere is going to have to be these spheres that I calculated inside. Okay. Now this is great, but let us use this component to generate more than just the simple sphere geometry. Okay. So let's use this component to generate spheres, to generate cones, and to generate boxes placed in the orientation of those planes, because spheres are great and they're nice, but what they do not really represent faithfully is the orientation of the plane in three-dimensional space. Because they're placed in the center and they have the same radius in every direction. You can only see the location really of the motion. But I would like to see how the user was turning his or her hand around, right? So that's why I would like to use some geometry that gives me a sense of orientation. So let me, for example, add here another output. This is going to be, let me turn off the visualization of this. I'm going to place here, I'm going to place a new input called cone, and here I'm going to place another output called box. All right, and then so that I can turn on and off the visualizations, I'm just going to plug in here this thing, and then the cones, and then the boxes. Okay. All right, sounds good. So let's now try placing cones on top of the planes that we just generated. So this is as the sphere generation, and then let's see, for example, cone generation, and this is going to be, do we have an object cone? I believe we do. Is that true? Yes. And the object cone, as you can see, I don't have overload, so the only thing that I can use to create a cone is the base plane, the height, and the radius. So I forgot the height. I'm going to add it as an input, but let me just hard code that for the time being. So that's going to be, for example, 0.1, and let me use the radius that I already have in as an input. And here on the outputs, cone is going to be equal to this element that I am creating. So I'm going to run this code, and this code runs really well, but then as I turn this on, you can see that I find this visualization much more interesting, because with the cones and with the tip, I can kind of see the orientation of the hand of the user as they were moving their hands in three-dimensional space. Okay? Which I think it's great. I actually like it a lot. And then, so let me add another input parameter here, for example, for the height. Okay? And that's going to be some value. I'm going to copy and paste this slider here, and I'm going to link that inside of the component. So this is not going to be a hard-coded number anymore. It's going to be some whatever data is coming in from the input. But this is not going to work because, and I forget doing this all the time, because I forgot to type that this has to be a double. All right. So now that it's a double, you can see that I have these really short cones. So I'm going to make the radius smaller, and I'm going to increase the height. And you can see how we have this like really spiky cone geometry on top of the plane. I kind of like this. I think it's quite interesting. So now, next thing, let's try boxes. So let's try placing boxes on top of these things. Okay. Boxes they take intervals. Is that correct? They take intervals. So box B is going to be equal to a new box, bounding box, base plane, intervals, etc. Yes. Okay. So that's going to be cool. Okay. For the boxes, I'm going to add two more inputs. So that's one of them is going to be width 1, for example. So the width in one direction and the width in the other direction. These two, I'm also going to make them double. So I'm going to copy paste here. Sorry, let me type them before I forget them. This one is double, and width 2 has to be a double again. I'm going to place 2 sliders here, and I'm going to use those 2 as the data for the width of the box, and then the height is going to be the direction, the dimension in the perpendicular direction to the plane. Okay, so that's great. Let me double click here and let me start working with the box. So I'm going to create a box using the box class that Rhino Common gives me. It's going to be called B, and then this is going to be a new box object, and then let me take a look at the overloads of what information do I need in order to create these box objects. I need something called bounding box, which I don't really have, so I'm going to keep going. I need either a base plane and 3 intervals for the x, y, and z size. I think that's going to be promising, but we don't really know yet what an interval is. I'll get to that in a second. A set of points as a plane and some other geometry, and a plane and a bounding box. So I think this is probably as close to what I want. I want to create a box on top of my base plane with x and y and z sizes. However, intervals are, why is Rhino Common asking for intervals? Let me actually draw a diagram and show you why that is the case. Let's go to the whiteboard. Okay, so let me open the whiteboard. And then, where is the where's everyone? Okay, here. All right, so let's say we have a plane like this, right? And then we have another plane like this, and then the plane looks something like this, right? That was a really bad. Okay, whoa. Okay, and we have the center here. That was a terrible center. Do I need that? Honestly, actually, I don't need that. I'm not even going to draw that. So a new layer. So, let me explain how this works. This would be, what would this be? Yeah. Okay. So let's go back to the whiteboard, and let's imagine that we have this plane in 3-dimensional space, okay? And this is the plane that we're going to be using for placing a box. If the box component, if the box class in Rhino Common only took 3 numbers x, y, z, it would be a little constraining, because basically what it would be doing is that we would be always forced to have a box on this plane that had equal dimensions on each side and equal dimensions going on in both directions on the plane. So we will basically be constrained to having a box that has to be centered perfectly on the plane. And Rhino Common is giving us a little bit more of freedom, because by asking us for intervals, what is allowing us is to place a box on top of this plane that is not exactly centered, that has some kind of offset from the center of the plane. So for example, if I wanted to draw a plane that looks something like this, a box that looks something like this, right? That was sitting perfectly on top of on top of the plane, so it was only growing in the one normal direction and was offset from the center of the plane. Then what's interesting is that this, for example, let's say that this side was 4 units. What we can see is that because it's starting somewhere already in the positive side of x, maybe the dimensions of this box are going from an interval from 2 to 6 in the x direction. So x is part of the interval from 2 to 6. And we can see that this has a length of 4 units in that direction. Similarly, in the y direction, we can see that this is also offset. So maybe this is 1 and maybe this is 3. So the y direction is part of an interval that goes from 1 to 3. So the size of the box in the direction y is 2 units. And then for c, we can also see that this may actually start at 0 if it's perfectly sitting on the plane, and the height might be, I don't know, 7. So c is included in an interval from 0 to 7, and therefore the box has a length of 7 units in the c direction. Okay, what this means is that intervals, can you actually see this? What it means is that intervals are actually really useful because they give us a lot of freedom, a lot of additional freedom when drawing boxes on top of a plane. So that's why what we're going to do is, even though we probably want, do we want? I don't know, maybe we don't want. What we're going to do is in our case, we're going to center the base of the rectangle. We're going to center it perfectly on the, let me draw what we're going to do. What we're going to do is, we're going to do something similar where we're going to center our box perfectly here on the plane, but we're only going to make it grow in one direction, so that with that we also get a sense of the directionality that the user had for the motion controller, because we can see all the bases being in the same plane. We can kind of see where the user was pointing, sort of. I don't know. Let's try and let's see how it looks like. This is part of the computational design iterative process. Trying things out, see what it looks, and then changing them if this is not what we want. So let's go back to coding. Okay, so back on the coding board. Now what I'm going to do is taking the width and the two widths and the height. What I'm going to do is I'm going to design 3 intervals for x, y, and z that correspond to a centered box in the width 1 and 2 directions, but then a box that only grows on 1 dimension in the z space. So that's what I'm going to do. I'm going to create 3 interval variables. So interval in x, and that's going to be a new interval that is going to go from minus 0.5 times width 1 to 0 times width 1. So whatever the width in one direction was, we want to start in negative half of that and positive half of that. Similarly, for y, I'm going to use here new interval of from minus 0.5 of the second width to positive 0.5 of the third width. And then for c, because we want the box to be sitting perfectly horizontal on top of the plane, what I'm going to do is I'm going to do a new interval that is going to start at 0 and is going to end at height. All right? And then I'm going to use those 2 intervals to say I want this box to be sitting on, let me go back so that we can see the overloads. I want to use these overloads, so that's why I'm going to start with the plane, then the interval in the x direction, the interval in the y direction, and the interval in the z direction. And I'm going to output that. What was the name of the output? Sorry, it was box. So box is going to be equal to the value of b. As I do this, it works. So I'm going to hide this, and I'm going to turn this on. And woo, what is this? This doesn't look what I was, okay, because the values were, so let me say this is going to be 0.5, this is going to be 0.5, and then the boxes are going to be 0.5, all right? Let me make this even smaller, 0.01, 0.03, no, sorry, 0.03, and then the height is going to be much larger. Can you see how interestingly, I like this a lot. Can we do, wait, can we do, Arctic view. Is Arctic going to work? No, because we haven't baked it. Let me bake it just for the sake of it. And let's see if we can do an Arctic view. Whoa, how cool is this, huh? So we're now getting this sort of geometry of bars. You can see how the bars are very thin in one direction, not so thin in the other one, and then they have this one dimension that is very prominent. So it looks like the base of the squares was the outer one. But this is, I find this really, really interesting. Who likes this? Can you vote? Can you give me an upvote on the chat? Okay. All right. So I think with this, we're going to leave this component alone, and we are going to move on to something a bit more complex. Okay. Well, actually, no. Before we do that, I would like to use the information of the button presses to either draw geometry or not, because we may, if this is, for example, imagine that this is a drawing tool, I would like to be able to take input, to take data from the user, which is if the user is pressing a button, it means that the user probably wants to draw something in space. But if they're not, then I don't want to generate this geometry. So let's implement just a very simple conditional statement where if the user is pressing the buttons, then we generate geometry. Otherwise, we skip that one. Okay, let's take a look at how to do that. All right, hey, Merit, how are you doing? Kartik, Arasto, whoa, what is going on? An interval is part of Rhino Common? Yes, very good. Arasto, so intervals, all of these that I'm using here, spheres, cones, intervals, boxes, all of those are objects, there are classes that belong to Rhino Common. So they're not part of vanilla Grasshopper, and we cannot use them, for example, in Visual Studio. If you look at my, where do I have that? If you look at my playlist of the lecture videos for Intro to Computational Design from last year, I actually have 2 lectures where I break down Rhino Common, what it is, how it works, what classes do we have available, what types of geometry objects, and I do quite a few examples of that. I actually think I do some similar examples to what I'm doing right now in these videos. So I also explain how to go to the Rhino Common documentation, and where is that? I also explain how to go to the Rhino Common documentation and read this, which can be a little daunting if you're on the beginner side of things. So check those videos out if you want to learn a bit more. Okay. Did I answer your question? If vanilla has something like, can we use that instead of the Rhino Common interval? In other words, that Rhino Common accept objects from vanilla C# classes, or it can only accept Rhino Common objects for something like a box? Yes, that's a very good question to Arasto. Anything in Rhino Common can accept vanilla C#. But the other way around doesn't work. Vanilla C# cannot accept Rhino Common objects unless you have figured out how to load Rhino Common as a dependency, as a library in a Visual Studio project, which is something that is very easy to do. So you can actually write console applications that use sphere, cone, intervals, boxes, etc. It's just that you can't visualize them, but you can have them as data. Okay. The only thing that you need to do is you need to load Rhino Common as a dependency, as one of your libraries in your code. Okay. Alrighty. What's next? Okay. So yes, I was saying true and false. Thus, this. So what am I going to? Touchpad pressed. Let me look at the data set. Oops, let me look at the data set. Let me look at the data set. Where is the data set? To see which one of, if I want to be used in motion 1 or motion 2. Touch. In motion 1, touch is true, touch pressed. Okay, so there are true objects here. So touch pressed here, but we're using motion 1. Okay, so let me delete all of this first. Now let me switch back to wireframe and let me plug in here number 1. And then I'm going to use this list here that has touch pressed. Okay, so let me explain how that works. Kartik, you mean legal as in like you could go to jail? Or as in it's possible to do with code? Yeah, you mean if it's legal as in you can go to jail, I believe the way it works, but don't quote me on this one, is that if you have a valid license, a valid Rhino license, if you pay for it, either professionally or with your educational license, you are allowed to use Rhino Common as a library in a project that you're working on. What you're not allowed is that if that project, you just want to share it with other people, or if you want to sell it, you're not allowed to distribute the Rhino Common library along with your project. So you could give people your code that depends on Rhino Common, but then you would have to tell them like, hey, you have to have your own Rhino Common, and then once you get my project, you have to link my project to your Rhino Common, and then you can use my project. But I believe that's how it works, but don't quote me on this one. I'm not a lawyer, and I have not read the full fine print of Rhino Common, so take a look at that, okay? Don't quote me on this one. All right. Okay, so now we were doing, Andres, you just moved the plane. You just move the plane, you just offset the plane, the height of the cone, and then you draw the cone backwards. Think about this. So where were we? Yes, we wanted to draw geometry or not based on the true or false. Okay. Okay. Okay, so we're going to implement that this component is going to render these boxes yes or no, depending on whether if the user was pressing some of the keys and the pads of the controller or not. So for that, I have switched to another data set, motion 1, which, because in motion 2, I just looked through the data and the user had not pressed any button, so everything was false. So here in motion 1, the user was pressing the button sometimes and then was not pressing it some others. So I want to show this so that we can see the difference between when the button was pressed and when the button was not. So here, right now, we're generating boxes and cones and spheres for every single object. Sorry, for every single plane, okay? But what I would like to do is I would like to implement a rule where we only render these objects, we only generate them if the user was pressing the button, okay? So there's two ways we can go about that. So first of all, here I'm going to create an input, and I'm going to say generate, and then I'm going to right click here and make sure that this is of the type Boolean, okay? And now I'm going to plug in the information for touchpad pressed, which I believe is the one that has both values, trues and false. And then as I do that, then there's two ways, there's actually a bunch of different ways to go about this. First of all, because this component, the only thing that it's doing is just rendering this geometry, we could do a very simple rule where we just say, look, if generate was false, okay? If generate was false, or if you want to shorthand, two double equals, okay? If generate was false, or we can shortcut this to say if not generate is true, then just return. Just don't do anything else in this component, okay? And if that's the case, then I can render this, and you can see how here and here we have some boxes that have disappeared, Let me see what would happen if I disconnect here. If I disconnect because everything is false by default, then nothing gets generated. So here I can plug this here, but I probably want to have a more nuanced control over the component where I say, I probably want to make this component work. I probably want to make this component not generate this sorry. I probably want to make this I probably want to control if the component cleans up the boxes that are when the user was not pressing the button or what it was. Why is this so difficult to say? Let me show you what I mean. What I mean is, let's call geometry. So this is going to be a true or false. Okay? So what that means is that I'm going to place here a button, for example, or a toggle. I'm going to place a Boolean toggle. So if what I'm saying is, if I want you to call the geometry, then I want to make this check. So I want to say, if call geometry equals true and generate equals false, then don't generate any geometry. All right? Now, if call geometry is false, then don't return and then execute all the geometry regardless of whether if what's coming in here is true or false. So what I'm doing with that is, so I forgot to do Boolean here, okay? So now with this, I'm calling the geometry, and then with this, I am not. I am basically ignoring the true-false parameter that is coming here. Okay, so with this, I'm basically saying, should I draw everything? Then call geometry should be false. If I want to just clean up the geometry, maybe I should name this in a different way. Clean geometry, for example, and then kill, for example. I don't know. And then if clean geometry equals true and kill equals, no, sorry, it should be generate. This doesn't make sense. If generate equals false, yeah, so this should be generate. And then I do this, I rerun the code. This is still called generate, and then I have the name generate that not exist. Yes, so this has not, yes, okay. Sometimes the C# component gets kind of blocked and it doesn't work. Okay, so you need to regenerate you need to restart it basically. So now with this, if I clean the geometry, then I remove objects that don't have a true here, and if I don't clean it, then I just draw everything. All right. Okay. So I think we're good with this one. I think we're going to leave this one component, the one that generates basic geometry. We're going to leave it like this. And I think I want to start doing something where we're going to plot geometry in a different way that is a bit smarter given how the acceleration of the motion may actually work. Let's see what that looks like. Alrighty. Okay, so what I think I'm going to do now is I'm going to draw lines, which is actually more difficult. It's a bit more involved than what we have right now. I'm going to draw lines, and then I'm going to place some rules about those lines growing larger or smaller, or by using, for example, a growing rule or a sine function, for example. Okay, so that could be interesting. Exactly, Arasto. That's going to be the third part of this video. For acceleration, we're going to measure the distance of each plane to the previous one, and then that's what we're going to use for acceleration. Okay? All right. So should I start this off already? So let me create here a plane. and let me create here a height. And then perhaps I can loft them. Can I loft them? Do I want to loft them? I think I want to do that later in the video. So okay, so that's going to be the plane. I'm going to turn this off. I'm going to turn the planes on, and I'm going to have the height, and this is going to be whatever Bologna value. And then I will give this some rules. I'm going to call it, yeah, height is okay. Yes. Oh no, wait, I cannot do height if I use just one single plane. Ah, interesting. Well, maybe I can start with a simple line and then I will turn this into an input that takes all those planes together. Yeah. Yeah, that's true. So maybe should I just do the line in the previous example? I think I'm going to do the line in the previous example then. I'm just going to generate it here, and then when I create this one, I will, and then the line for the line, I'm going to use the height. And here I'm going to talk about taking all the planes together as a list. I think that's what I'm going to do. Yeah, that makes a bit more sense. Okay. Okay, I'm going to take back what I just said, and before we move on into more complex forms of plotting motion, I'm actually going to add another object to the simple objects that we have used, that we have placed here, which is going to be a line, just simple, easy vertical line from the plane in the normal direction. And actually I want to do that because that's going to involve a little bit of vector algebra and vector manipulations, which I think is super interesting. So let's do that. I'm going to add here another component, another output that's going to be a line. And I'm going to place a geometry box here so that we can visualize it as soon as I do it. And then I'm going to double click here and I'm going to say, well, I'm going to now create a line. I'm going to create a line that is going to go from my base plane to another point, to the center. It's going to go from the origin of the plane to another point that is going to be at the height distance of the plane. But actually, before doing that, let me show you how we're going to do this on the whiteboard. Okay, so now I'm going to go. This is the whiteboard. Okay, so where is my mouse? Okay, here, okay. And okay, so we have this. I'm going to create a new layer. And before we create this layer, I'm going to create. Oh, no! I'm going to create this here. So, and then I am going to draw on this plane a third axis. Oh, that was a terrible axis. Okay. Now, I don't want it to look that it's... Okay. Wow, that was bad. What is wrong with this axis? Okay. All right. And I think with this I can start drawing, because what I want is I would like to create a... Okay. Let's go back to this plane in three-dimensional space that we were looking at before, and let's bring back to our minds the fact that this plane is made out of two main vectors. The x vector, here represented in red, and the y vector represented in green. And because they're both unit vectors and they're both perpendicular to each other, then I know that it's very easy to understand that there will be a third vector, the vector z, represented in blue here, that is perpendicular to both of them and is also unit. Okay, so that is the normal vector of this plane, or the z vector of the plane. What I would like to do is I'm going to generate a line that is going to be perpendicular to this plane. Okay, and the way I'm going to do that is because I'm going to create a line between 2 points. The first point is going to be the origin of the plane, and the second point is going to be a point that is perpendicular to this plane at a given distance. In this case, I probably want to be using height. So my other point is probably going to be somewhere here. But the thing is, in order to generate the line, first I will need to generate this second point. And this second point, how can I generate it? Well, it turns out that it's very easy. I can just take this z vector, the vector of the plane. I can take this vector and then I can multiply it by whatever the height, so that I can create another vector that has the length that I want. And then what I can do is I can take this point and add this vector to find the second point in three-dimensional space. And once I have those 2 points, the origin and the other point that I have moved with the scaled normal vector, then I can very easily create a line between those 2 points. Okay, so I think that's what I'm going to do. Let's go back to the code. So if I go here, you can see that I can create from the plane object. So from plane, I can access a lot of information. I can access the x-axis, the y-axis, or the z-axis. That is the normal one. And I can also access, for example, the origin. That is the point at the center. So what I can do is I can say, for example, let me create a new vector 3D object, which is going to be the translation vector. That is the vector that I'm going to use to move the origin at a particular height. And that's going to be the plane.z-axis. And what I'm going to do is that I'm going to multiply that vector by a scalar, by how far I want to scale that vector. Because I know, and this is a Rhino common thing, I know that this z-axis is a unit vector. So if I multiply by height, I know that I'm going to end with a vector that has that length, the length of height. And now what I can do is I can create another point, and I'm going to call this my endpoint, the endpoint of the line. And that's going to be equal to the plane, the origin of the plane, so that's going to be plane.origin, that is the point at the center of the plane, plus this translation vector that I have created, because I can move a point by taking the coordinates of those points and adding to those coordinates the coordinates of the translation vector that I want to move the point by. That will give me now 2 points, and that I can use to say I'm going to create now a new line. And you can see that I have point from and point to, point start and vector. Actually, I could have used the vector right away. I didn't really need to use the endpoint, as you can see here from the constructor. But oh well, I've done it already. The direction vector and the length. So actually, I had a lot of options. So let me just stick to the end starting point and the end point. So that's going to be plane.origin. That's the start point. And then the other point is going to be that end point that I just generated. And therefore, if I do that, now I can output that line object. Let me see if everything works here. It looks like I get no errors. And then if I visualize this, I can see that I have all these lines that are going from the center of the planes to these other points that I've generated in space at a distance of height. And if I move this, you can see how all those points, all those lines, adapt based on that distance that I have defined as height. Okay, so yes, I wanted to do this line, this simple line, and I wanted to break down the algorithm for generating the point. because I will be using this line generation method for some of the next exercises, now the next tests that I'm going to do to visualize this. Okay, so let's move on now to taking all this and visualizing the motion in a bit more complex way by linking together all those planes with some kind of logic among themselves. Alrighty, how was that? Can you give me a thumbs up, thumbs down? Okay, so where were we? Where were we? We were, yes, we were going to do a component, and this component now is taking planes. Okay. Okay, so maybe I can start. Maybe I can start by doing just a simple polyline or an interpolated curve over those points, and I can also plot the lines, and now I will want to do lines that somehow have a larger or a smaller distance based on some parameter. So, for example, how far off they are along the curve, or based on a sign. So that's going to be cool. That's going to be pretty cool. Let's get to do this. What I would like to do now is to start creating geometry that is not just, for example, single boxes or single cones or single circles or single geometry objects on top of each one of these planes without relation to each other. If what we're trying to visualize is fluid motion, I think there should be some relation between the objects that we are trying to visualize. Okay, so what we're going to do is we're going to now create a couple of tests where I'm going to draw simple geometry like polylines and lines on top of these planes, but I would like to relate the dimensions and the position of these objects to the other objects that are in this collection. The difference of how we're going to approach this is that if you remember in this component here, what we did is that we created the C# component and we dropped we dropped the component, and then we said, oh, we're going to take all the planes here, but we're going to take them one at a time. Why did we say that? We said that because when we dropped the component, and I said, for example, here, this is going to be plane. I said plane before. What I said was also, I'm going to make sure that this is of the type plane, but here, let me make sure that this stays as item axis. Because before, I only needed one plane, because I was going to be creating one circle, one cone, one line, whatever. But because now what I want is I want to relate, and I want to create an algorithm that makes elements different based on some relation with the other elements, it's not going to be enough to just work with each plane at a time, as I was doing here. If you remember here, the input of this component is just one single plane. And therefore, with each plane, I don't have access to the information of the other planes. I only have access to one plane at a time. And therefore, I cannot make calculations, or I cannot know when this plane, how far off on the list it is, etc., etc. So in this case, it will be very important that now I'm going to start working not just with each instance of a plane, but I'm going to work with all the planes at the same time. So what I need to do here is I'm going to right click, and I'm going to say, instead of accessing each element at a time, I want to access the whole list of the planes. Okay? And look at the difference. If I now double click here, instead of one single plane element, what I do have is a collection of planes, a list of planes. And therefore, this will give me access to much more information, such as, for example, how many planes are there in this list. For every plane that I use, I will know if it's the first one, the last one, the one in the middle, etc., etc., and I will be able to make smarter decisions. On the flip side, I will have to write more code because I will have to use for loops and iteration to go through all of those and create lists of data. But with great power comes great responsibility, or a lot of tedious writing code. I don't know. You name it. But I think that this is a much more interesting approach because it's going to allow us to do things that are more interesting. And the first things that we're going to do is just going to be something as simple as creating a polyline between the centers of these planes. Something that we couldn't really do before because we only had access to one plane at a time. So let me here create an output that's going to be a polyline, and another one that is going to be a curve, because we will also do a smooth curve across all these planes. So now I have all these planes here, and then what I'm going to do is I'm going to create a polyline object, poly, and I'm going to initialize this to a polyline object, and let's take a look at what are the inputs for the overloads. I can start a new polyline, I can give it an initial capacity, or I can give it a collection of objects to start with. I actually don't remember how this works, so give me a second that I'm going to look this up on the documentation, and I will be right back. Ice cream with grasshopper? What is going on there, Parastorm? I have no idea what you're talking about. Okay, let me look at the documentation. Rhino Common, and let's take a look at where polyline is. Polyline, the polyline class. Okay. Okay, so it takes a collection of points, so that is fine. So then I can just save myself all the hassle. Okay, and then at the same time, let me look up curve. The curve class, or interpolated curve. How is that? I always forget. I always have to interpolated curve. Create interpolated curve. Curve, not style, vector 3D. So I can create a interpolated curve from a collection of points, the degree, and the curve not style, which is, what is this? Uniform chord, uniform periodic. All right. Okay, so okay, so I'm going to start here. Okay, so I have looked up the polyline class in the Rhino Common documentation, and what I can see is that I have a better explanation of what the three overloads for the constructor are. A new empty polyline, a polyline with a capacity, or a polyline that can take a collection of point 3D objects. IEnumerable is like, it's an interface for anything that can be iterated over. So this could be an array, or it could be a list. So because I have a list of planes, I think I might be good to go with this, but let me take a look because sometimes parameters that accept planes, they also sometimes accept points instead. So let me try first if this is going to take a list of planes as opposed to a list of points, which is what I can see in the documentation. And then so polyline equals poly, and then if I run this code, it's probably going to crash, right? Yes, because it cannot take a collection of planes instead of a collection of point 3D objects. So what I'm going to have to do is I'm going to have to take all the planes, and from each one of them extract the origin into a new list that I will be using for generating this polyline. So let's do this first. Let's take all origin points. So I'm going to create a new list of, it's going to be called origins, and it's going to be a new list of point 3D objects. Okay, and then with a for loop for int I equals 0, I is less than planes dot count I plus plus, I'm going to say to the origins list, can you please add for each one of the planes its origin? All right. Does this work? Let's see if this works. Okay, so is this not working? The name poly does not exist. Okay, so this part is working. So I have generated a list. I have generated a list with all the origins. So now I should be able to feed that list here to origins. So I'm going to say click, and then yes, I have that. And then can I actually see the polyline? Oh well, I haven't really even plugged in the planes yet. So planes, and then boom, interesting. So you can see that I do have that polyline, and the polyline actually looks pretty smooth because basically the planes are so close to each other that it looks pretty smooth already. Okay, so this is great, and polylines are great, obviously. I'm going to, just for the sake of showing you how it works, let me also create a simple interpolated curve over all these planes. So this would be analogous to using this component here, the interpolate curve, through a set of points. I was looking also at the polyline, at the curve, at the method to do that before, and this one is a little different because this one is a static method, so it's not going to use the new constructor syntax. It's going to be using a little bit of a different syntax, but the inputs are very similar. It takes a collection of points, it takes the degree of the curve, which by default we're probably going to be using 3, and then it takes this thing called the curve not style, which if I click here, it tells me that this is an enumeration, which means that it's a list of values that I can choose from by their name. You will see how that looks when I write this here on. So I'm going to say here that I'm going to say I want a curve. I'm going to create here, I'm create polyline. Then here I'm going to say create curve, and then I'm going to create a curve object, C for example. And instead of using the constructor as I use with regular classes, for this one, because it is a static method, and I haven't recorded a video on this yet, but I will do at some point soon. Just feel free to check my Learning C# playlists. And then the way I call static methods is by calling into the class and accessing all the static methods that belong to the general class instead of to a particular object. So here you can see that I can use create interpolated curve. I open parentheses and I got my list of points. So that's going to be my origins and the degree. So I have a constructor that requires that I don't really need to input the dots, the not styles or the tangencies. So that's fine. And then here on curve, I'm going to output this C object that I have created. So I'm going to go here, and then I'm going to close this. I'm going to copy paste this, turn this off, and then yes, and then this is my curve. What you can see from this curve is that it's actually a bit smoother. It's very difficult to see because the polyline had a really good definition, but you can see that it's actually curvy in between the segments of the polylines of the planes. So, yep. So this is how you create geometry between the planes, because you change the input so that you have access to the whole list of elements, and then you can operate with them as a whole collection. What we're going to do next is that I'm going to now generate lines on top of these planes, but I'm going to start playing with the dimensions of the lines and make them different according to different rules, okay? And we will see what those rules can be, okay? Let's take a look at that. Alrighty, I need 1 minute. I need to go to the restroom and I need to take some water. Okay. How are we good so far? Okay. So let me take a quick break. I'll be right back. Just 1 minute. Okay. Don't go anywhere. Okay, I'm back. Okay. Do we have sound? We have sound. Yes. Okay. And where were we? We had curves. Okay, so we had lines. Um, okay. Okay, we want to generate. What are we doing now? We're creating perpendicular lines, but then we're giving them some kind of variation. Okay. Okay. The next thing I'm going to do is we're going to create perpendicular lines to these planes. And for that, I'm going to, first of all, I'm going to add another output here, and this is going to be called lines, for example, and I'm going to give it an empty box to display that geometry, and then I'm going to copy the code that we had here, line, to generate the line. But what I'm going to do is that this time, because I'm going to be reusing that code a lot, whenever I think I'm going to be reusing code inside of a for loop or inside of or in many places, it's actually quite convenient to create a function to encapsulate that code. And even though this is not very complicated, it's just 3 lines of code, but it's still a good practice. So what I'm going to do is I'm going to create a function call that I'm going to call line perpendicular to plane. Okay, and then the input is going to be a plane PL, and then the double is going to be the height. Okay, and I'm going to open parentheses, close parentheses. I'm going to paste this code here, and I'm going to make sure that the return type is a line object. So whoever somebody calls this function with a plane and a height, they will be getting a line in return. So here, I'm going to be saying I'm going to be creating the translation vector from that plane and that height. I'm going to be creating the endpoint from this and this, the line with these 2 objects, and then I'm going to be returning L. Does this work? Do I have any typo of any kind? No. This copy pasting was fine. So yeah, so I have this function. Anybody who calls it with a plane and a height will be getting a line that is perpendicular to that plane and with this height. Now very simply, now what I want to do is I want to spit out from the component a list of lines that are perpendicular to these planes here. So I'm going to take input here. I'm going to say, for example, maximum height, and that's going to be of the type double, and I'm going to plug in here a slider from 0 to 1. Okay, and now, because instead of one single polyline or one single interpolated curve, what I want to output now is a collection of lines, 1 per plane. What I would need to do is I would need to say, let me first create a collection of lines. So for example, that is going to be called lin, for example, and it's going to be a new list of line objects. A new collection of line objects. And then what I'm going to do is, with a for loop, I'm going to iterate over each one of the planes and then create one line for each one of those planes. So I'm going to say for int I equals 0, I is less than planes. And actually, you know what? Why don't we try a for each structure? Because this is a list of planes. We can iterate them with this special for structure, loop structure that is designed specifically for collections. So for each plane P in planes, why don't we generate a line L, which is line perpendicular, there's a typo here, line perpendicular to plane, and then that's going to be plane, and that's going to be max height are going to be the 2 parameters. And then to line, I'm going to add L. Okay, this code works, it doesn't break anything, and then I'm going to, as the output, I'm going to pass this collection of lines. Let's see if this works. Okay, I have a collection of lines, they're all perpendicular, and they all have, I can control their sizes. So this is very similar to what I did in the component here above. What's interesting is that now, because I have access to all the information of the whole collection of planes, I can now start playing a little bit with creating variation among these lines. So for example, instead of making them all have the same height, I can find a rule to say how high each one of these lines is going to be. And what I would like to say, for example, is I'm going to start with a very simple rule. I'm going to start from lines that are going to be very, very short. So it's going to be 0 height at the beginning, and they're going to increment linearly all the way to the last line, which is going to have maximum height. Okay? So what I will need to do is I will need to say, for each plane, I need to find how far off on the list of planes it is. So if it's the first one, if it's the one in the middle, or if it's the one at the very end, and given how far off it is, that is going to be the ratio of the maximum height that I'm going to use. So how is that going to work? Let me show you. So first of all, we're going to get rid of this for each structure that I created, because it's very easy and very simple to read and write. But the problem with this one is that we don't really know while we are inside of the loop, we don't really know at which position of the iteration we are. And in this case, because we want to know how far off on the plane list we are, we want to have that information. So I'm going to replace this completely, and I'm going to replace this with another with a for loop of the typical kind. I is less than place.count and I plus plus. And to make the rest of the code work, I'm just going to say plane p is going to be equal to the plane in the list at position I. Okay? So that's fine. And so this is going to work, and this code still works, no problem. The only thing that I would like to do now is I would like to make sure that I know how far off along the list of planes I am. So what I'm going to do is I'm going to figure out a rule where I'm going to design one value that is going to be I'm going to call the factor, and that value is going to go from 0 to 1. And 0 is going to correspond to the first element on the list, 1 is going to correspond to the last element on the list, and anything in between is going to just grow linearly. 0, 0.01, 0.02, 0.03. You know where I'm going with this. So in order to do that, I'm going to create a new variable called factor that I'm going to calculate inside of the for loop, because this factor is going to change for each one of the planes. And with this, I want to calculate how far off on the list of planes that I am. So because I know which plane I am on, and that's the value of I that goes from 0 to whatever value, what I can do is I can say if I divide the value of the position at which I am by the total position, so if I had 100 elements, it would be 0 divided by 100, 50 divided by 100, that would be 0.5, or it would be 100 divided by 100 would be 1. Okay, so if I do this and I divide this by planes.count, what I can know is how far off from 0 to 1, in a scale from 0 to 1, I am on my list. And if I use that factor to multiply max height, then I will start getting heights that are increasingly large, all the way up to max height at the end of the list, at which point this factor is the value of 1. But this is not going to work. Let me show you why not. I'm going to press OK, and then I'm going to get 0 length lines all the way through. And this is because I may or may have not remembered one property of the C# programming language, which is that when you divide two integers together, such as I and count, the result is also going to be an integer. And it's going to be the integer that is rounded down, which means that any number from 0 to 100, for example, divided by 100 is always going to give me 0. So what I need to do is I need to force one of the two values to be a double. And I can do that by casting it on the fly like this. I can say, can you just convert temporarily for this calculation? Can you convert count to a double? And then if one of the two numbers is one double, then the result will be a perfect real division. If I do this now, take a look at how nice this is. The first, let me turn off the planes, and you see how the first planes start from 0, from like very small. It looks like there's a very large concentration of planes here, and then it starts growing and growing and growing all the way up to 1 unit, which is probably where we are here. Now, 1 unit would be this. All right? So you can see how these planes, these lines have been growing over as we went. Okay. So that is one rule that we could implement. Another rule that I like, for example, is using a sine function. How does that work? Well, we can use a sine function and say we also can know how far off along the list of planes we are. If instead of using that as a factor of the height, I use the sine of that as a factor, then I will be having a value of the height that is oscillating between 1 and -1. So if I can do that, what I can say is, how about I use the math dot the sine of this value? Okay? How if I use the sine of a value that goes from 0 to 1? That could work, but it's not going to be great because in this case, because the value goes from 0 to 1, that is going from 0 to 1 radians, which means that it doesn't really let the sine do a full cycle. A full cycle of the sine function, a full cycle of the sine function. Let me actually use the cosine, which starts with 0, which starts with 1 as the first value. If I use the cosine, you can see that it doesn't really decrease. But what I want is, actually no, let me use the sine because I want to start at 0. I think it looks a bit nicer. So what I want to do is I want to make sure that I cover the full spectrum of sine waves, at least all across the planes. And we know that the sine function does a full up and down at 2 pi lengths, or 1 tau lengths, okay? The full period of the sine curve is tau units long. So if I take this value here, and before dividing it, I multiply this by 2 times the value of pi, then I will make sure that I am doing a full one. It is a little difficult to see. Let me see if we can see it like this. So we have the lines, and you can see how the lines start at 0 here. They go full positive 1 more or less around here. Here they go negative. They go all the way to full negative 1 here. And then they close up here back at 0. All right? This can be easily seen, I think, if we also turn on the polyline. Can you see the polyline? You see how we go all the way to positive 1, then here it clamps at 0, and then here we go to negative 1, and then it goes back to 0. I think this curve is a little weird because there's definitely a large concentration of planes here. So let me switch to the other one and see how that looks like. If I use the other one, this one is a little more convoluted, but this one looks really cool as well. This one is so fast that it's a little difficult to understand. But yes, we see the inflection point here at 0. And then the starting point, which I believe is somewhere here, starts at 0, maxes out, and then it ends somewhere else that I can't really see. Okay? Yeah. Okay, so we can use we can use a rule like increasing lengths. We can use a sine function, or, and this is probably the coolest part that I wanted to get to, we can use something that relates a bit closer to the spirit of the curve and to the spirit with the motion, which is the actual speed or the actual acceleration that the user was putting into the drawing as they were moving this around the screen, around the 3D space. Okay, and this is actually quite clear to see in a way. If we go back to the previous, to the two versions that I have here, you can see how here there is a very large density of lines and planes, and here we can see how that density is much less. So visually, it's kind of easy to understand that here the user was probably moving the controller much slower, and actually this whole distance is pretty small, but then the user all of a sudden sped up, and then this whole length here was a much faster motion. Okay, we were able to see this because of the concentration of lines here, but also because if we understand that the sine function zeros at half the period of tau radians, right? We can see that half of the time, like of the user was recording, by half of the time the user was still here, but then after the other half of the time it just moved a really large dimension. So clearly the speed of the motion increased after this point here. So that we can read from this geometry, but I want to find a way to make this even more explicit. This is kind of the beauty of exploring geometry and data by visualizing it in three-dimensional geometry. So what I would like to do is I would like to now find a rule to make the lines, to make where they are, or how long they are, related to the speed of the motion. But how can I know the speed at which the user was moving? Well, it's actually a fairly easy. It also draws from the visualization that we have here. We can think that the user was slower here because we see a much larger concentration of lines in this area. And larger concentration of lines means that if we assume that the controller was recording positions at a regular interval, it means that the distance between these points is much smaller at this area where the user was going slower than the distance from these points. So a nice rule that I will be able to apply will be, in order to calculate the length of this line, instead of just using a random, like a sine function or whatever, why don't I just calculate the distance between the plane that I am and the previous one, and then use that as the factor of the line that I'm trying to draw. Let me show you how I would do that. Okay. Parastorm 2pi. You could have only said Python to make things work, to make this worse. Arasto, we're about to finish to integrate what you were trying to tell before. Okay. All right. Water. Is the audio working? Is everything fine? Yes. Okay. So, okay. So what we're going to what we're going to do is we're going to go to our component, and then here, where we calculate factor, let's just get rid of this for the time being. Let's just cancel this out, okay? And then before we do anything, what I would like to do is I would like to calculate for each one of these lines. I would like to calculate the distance between the plane that we're at and the previous one. So what I would like to do is I would like to say, well, let's take a look at the distance, and let's say I'm going to calculate the distance between, sorry, I'm going to say P is going to be the current plane that I'm iterating over. And then I'm going to fetch the other plane, so that's going to be previous plane, and that's going to be from planes, is going to be with the position that I am minus 1, okay? And then I could theoretically calculate the distance between these two, but if I run this code now, it's going to fail because I started counting with the very, very first plane. And if I do that, then there's really no plane before it. So there's no plane in position minus 1 on the array, and then my component fails. So what I will need to do for this particular rule is I'm going to need to discard the very first plane, and I will start working with the immediately one afterwards. So I'm going to start here with the number 1. I'm going to run this code, and then now I am good. I'm not doing really anything yet. But now what I can do is I can say, let me calculate the distance between these two planes. The way I'm going to do that is I'm going to say double distance is going to be, how did I calculate the distance? It was, yes, from the origin. There's a function, there's a method in Rhino Common. So I could do the Pythagorean theorem. I could find the XYZ coordinates of the two origins and do the square root of the squares, the differences, etc. But there's a shorter function for each point. The point class has a function called distance2 that I can use to calculate the distance from one point to the other. So I want to calculate the distance of the origin of P to the origin of the previous plane. So that's going to be previous P dot origin, previous P dot origin, dot origin. That's it. And then that is probably what I would like to use now here as a factor. So instead, sorry. So just because I don't want to delete code, I'm just going to say factor is going to be equal to the distance, for example, to that distance that I just calculated. Okay, and then I'm going to add that to I don't know what I'm doing here right now. I'm cleaning things up. Okay, and then here I want to say that this is going to be equal to max height times the factor. Okay, and ooh, something is not working, or is it working? Let me crank this up. So it turns out that the distance between these things is actually a very small value, except for here. For some reason, there's a large jump here. Where am I? So let me crank this up to a larger scale. So this is going to be 10. So now if I scale this up, you can see how these points, these lines, are now representing the distance between consecutive planes. And you can see how here those distances were very small. There's a very long jump here. So for some reason maybe the HTC was not recording properly, or there was like a jump in the calibration. And here it starts increasing all the way up to this area where we can see that these lines are very long. And then it also reduces again back by the end of it. It looks like there was a drop in the speed of the motion. All right, so let me plot the other one to see how that looks like. Ooh, this is very nice too. This is kind of nice, huh? So you can see here it was slower, here it was definitely very fast, and then anywhere in the middle it was like going up and down. Okay, this is a really cool visualization actually. And I think what I want to finish with is that we probably want to create a visualization that is now showing me this kind of speed graph. So imagine that this was a linear graph, and we had like a graph of like speed up and speed down, like when you go running with Strava and it gives you like your velocity. Something that I can do is I can take the end points of all of my lines, and then I can create another polyline that is just that is like the graph of the speed of these points. So let me polyline with from speeds, polyline with speed of the motion. And then, for example, I can say, let me create a graph points, and that's going to be a new list of point 3D objects. I'm going to create a list to store. I'm going to create a list to store the endpoints of those lines. So now I'm going to iterate for each, and for this one I can use a for each line L inside of lin, that is the list of lines that I just created. Take graph points and add from lin, add the end point. So point at start. So the point is called point 2. That is the end point. Okay. So from the line L, I can just write it here from line L in lines. So in the list that I had before, take the last point and then add it to graph points, and then create a new polyline. This is going to be graph. I'm going to call it graph, and create a new polyline from all these graph points elements. Graph points, yeah, and that's it. So does this work? It does work. No, so no errors. And then I'm just going to create a new output, and this is going to be lines, and this is going to be the graph poly, for example. And I'm going to copy and paste this here, and then to graph poly, I'm going to assign here. I'm going to assign this graph, this polyline that I just created. And now you can see that I have this sort of closed curve, kind of. I have the base, I have the graph, and you can see how one is like a smooth polyline that represents the motion, and the other one is like a very jagged polyline that represents the speed at which the user was going. A really interesting exercise would be to now take all of these values and then just unroll them over an X and Y axis and then get a graph of the speed of the motion over time. You know, that could be a really interesting exercise to do, which at this point, I think I'm going to leave it up to you, the user, if you want to try, because I think this video has gotten a little long already, so I think I'm probably going to wrap this up at this point. Give me a second to think if that's the case. Why did I read your mind, Kieran? that the video got a little too long? Or no, or the unrolling part. Okay, so I think I'm going to leave it here. Okay, so maybe that's the coding challenge that we have for this week. I don't know if I'm not sure if you've been here with us before, Kieran, but we have offline coding challenges every week. So maybe that could be this could be the week of this challenge, just unrolling that curve and visualizing it as over X and Y. That could be really cool. Okay. So I think with this, I'm kind of cool. Yes. Well, can I create a loft between these lines? That's probably not going to take too much, right? Loft. Where's here? Loft type create from VREP, create from loft. Is this going to be a pain in the ass? Nah, I don't think so. Well, will I be able to use the lines as curves? Okay, let's just do the loft, and that's it. Okay, yeah, let's do that. Okay, before we wrap up, I'm going to do the last exercise, which is going to be just taking what we have, this collection of lines that move over the motion, and then create a loft surface over these curves. Because the problem is that I have all these lines which look great and they look super nice in 3D, but if I were to do like a shaded or like a rendered version of this, I could not get a solid representation of this motion and space. So for that, I need some kind of loft surface, which is very easy to generate, for example, as a loft of all these curves that I just generated. So for example, this, I'm going to create here another, I'm going to create here an output that is going to be called loft. And then I'm going to go here and I'm going to say, I'm going to create a loft object. And the way that's going to be is that I'm going to use the static method from the VREP class called create from loft. And it's going to take curves, and it's going to take optionally starting and endpoints, and you will see that I will not use them, so I will set them to point unset. And then it's going to take which type of loft you want to use and whether if that is close or not. So let's take a look at how that would work. So this is going to be VREP. I always forget if it's not double capitalized, it's just one capitalized, and that's going to be the loft. I'm going to call it surface. Okay, so this is going to be vrep.create from loft here, I'm going to open parentheses. I'm going to pass in a collection of curves. So that's going to be lin, the collection of lines. So now this is going to be a reference starting point and end points. I don't have those, so I can set point 3D to unset, point 3D to unset also for the end one. Loft type is an enumerable, so it allows me to choose from a list of predefined options. So I'm going to just choose normal, so loft type of normal, and I don't want it to be closed. So that's going to be it. And let's see if this works. I'm not sure if it's going to work. I think I may have to cast the lines to curves. Let's see. I'm going to run this, and then let me see what the problem is. I cannot convert from a collection of lines to a collection of curves. Exactly. So I'm going to have to do a process before where I convert the lines into curves. So I'm going to say, okay, so curve lines, that's going to be a new list of curve objects. A new list of, oh my God, a new list of curve objects, all right? And then for each line object L inside of lins, let please to curve lines, let's just add this element, convert it to a curve object, to a NURBS curve. Okay, and if I do that, I should be able to run this code. I still have the same problem, exactly. And then what I need to do here now is do curved lines instead of simple lines. And if I do that, it turns out that I may have done that loft surface. Is that true? I have, yes, exactly. I have that loft surface that I can now use for rendering or for visualization of any other kind. I can bake it, for example, and then I can use the Arctic representation that I personally like a lot, for example. So I can see this. But actually, let's try the other one. I think the other one, the other CSV file is going to look much cooler than this one. Let me delete this. Let me visualize this, and let me bake it. And then as I bake it, you can see how we have this like ribbon that is folding on top of itself, and it's the collection of all the speeds of the object. It looks like a desert rose of some kind, which I think is pretty neat. And I have here the one polyline and the other polyline. No, that's the other. This is the one. So that's kind of neat, huh? How cool is that? All right, well, I think that with this and the sun that is entering through my window right now, I think this is where I wanted to end today. I hope that with these pencil shavings I'm getting from the chat, that's a really good analogy as well. You're right. It looks like pencil shavings. But yes, so I think this is where I wanted to end. I hope to have made a case about the exploratory nature of computational design, how we can take geometry and how we can start like playing with it and finding relationships between objects that we can then plot in three-dimensional space. I have not covered in this video other things such as, for example, taking the two planes of the controller, because remember the user had two controllers and there's always like a pair of planes for each kind of motion. So I could have played with joining those two planes with lines or with or representing them well, it's getting really hot here, or representing them with some kind of geometry in between them. And I have also not gone over, no, I think that was pretty much what I wanted to do. I also left it as a challenge for you, to the user, to take this graph of the speed of the motion and then just unroll it and plot it as a 2D graph in the XY plane to just visually see the evolution of the speed of the motion, which is also a pretty interesting exercise that I'm not going to cover with this video. In any case, if you like what you saw and you think this is useful, and if you want to see more, just please click on subscribe, notifications, follow us on Instagram, Twitter, whatever your jam is, and stay tuned. We do this live every weekend, sort of, more or less. Yeah, so that's it. My name is Jose Luis. Thank you for being here, and see you on some other algorithmic modeling challenge video or whatever you like. Thanks a lot. Okay, and we need to record the introduction. So for that, I'm going to close the window. And we need to record the intro, which is what? What if I turn this into a wireframe? Spunky Dead Cat? That is a majestic nickname. Thank you, Spunky. All right, so let's. So where was I? Okay, so introductory video. Okay. So, so what am I going to say? I'm going to say that this video was about taking a data set of motion. Do I have the data set here? Where is this? GSD 66. Okay. Well, I did explain that in the video, right? Okay. And I have to explain that it's a continuation of the other videos where I did CSV reading from scratch. And now that I have this, I'm going to show how to plot different types of geometry on top of this. So for example, planes, oh no, planes, boxes, etc. I may just use cones, for example. Or spheres. No, spheres is very heavy. Nah, whatever. I'm just going to cut to the chase and show the cool stuff. That's what I want to do. Okay. Hi, my name is Jose Luis, and I am welcoming you to another algorithmic modeling challenge. In this one, what we're going to do is, this is a continuation of a set of videos that I recorded previously, where I took a data set of the motion of a gameplay controller, so an user that was using two game controllers that he or she was moving in three-dimensional space, and then where all the motion was recorded as a CSV file. In the previous video, I showed how to write a C# component that took this CSV data and turned it into planes in three-dimensional space. And then in this video, what I would like to do is I would like to explore all the possibilities that we have to visualize this motion in three-dimensional space. So I do things as, for example, converting, placing boxes and placing spheres and placing cones on top of that geometry. But most importantly, I end up doing an exercise where I try to plot as a collection of polylines and lines and graphs. I try to plot the speed and of the motion of the user, ending up in this kind of really interesting object of desire of some kind, this kind of like pencil shavings, desert rose or whatever. I don't know what this is, but I thought it was very interesting as the visualization of that motion. So in this video, I will explain how to take planes, a collection of planes, and how to populate them with geometry, but also how to create geometry that represents the relation of those planes between them. Like, for example, the speed of the motion of the user. Okay? So without further ado, let's start and let's write some code and see how we can enjoy this. This video is going to be a bit more exploratory. I don't have a really, when I started, I didn't really have a goal, and I ended up here. So it's a bit more different than the regular algorithmic modeling challenges where there was a very clear goal. This is more about the process of exploration and finding what could we use the data for and how could we visualize it. So I hope this also helps you as part of your computational design iterative processes. And let's talk in and more coding. Let's get to it. All right. Woohoo! Oh, okay. That's being a long Saturday. Alrighty, people. How's everyone doing? How are you holding on? I am beat. I'm ready to start the weekend. Oof. So I can stick around for a few minutes. If anybody has questions, comments, requests, whatever. I want to remind people who may have gotten here a bit later in the recording that we have a Discord channel where we share stories, where we talk to each other, where we share coding challenges, and where we do like offline social life in between live streams. I do a few announcements here and there also in the Discord. So if you're interested in what we do here, feel free to follow us on the. Feel free to join the Discord. And okay, loving the C# series. I like that you're loving it, Rafael. And this was not exactly part of the series, but it's more like an exercise of what you could do, knowing what we know already from the C# series. Andres, if you want to use this data for the motion of a robot arm, how to scale the data in C# or remap the data inside of a bounding box of intervals to fit the workspace of a robot. Rafael, I don't know which question you did before, so if you can post it again, that's perfectly fine. Andres, so you can remap this. You can remap this very easily. So these are planes in three-dimensional space. Literally, if you scale by any number the origin of where they are, you can basically scale the space at which they occupy, and you can also move them around. You can use the robot to reach just the center in whichever orientation, and if you do that, then the robot will have a lot of freedom to reach that with whichever orientation. But if you want to reach that target with the exact orientation that the plane has, then you will be a bit more constrained because there will be situations where the robot will not be able to reach that position because it will be out of range or it will be out of the kinematic space that it can reach. So in those cases, you either have to very carefully make sure that the motion that you're doing with your hand is one that then, once you scale it up, can fit the workspace of a robot. Or alternatively, you can do checks where if the robot is about to reach a point that it cannot reach, then you make changes to that plane so that it starts fitting within the dexterous area of that robot. Hopefully at some point we get to doing exercises like that. We're not there yet, I think, but hopefully sometime soon, because I teach a lot of robotics, so I really need to create content like that for my own teaching as well, right? Rafael, I wanted to ask was if it makes any sense to use custom classes in Grasshopper workflows. Like I usually just use the tree structure, but I could, for example, create a building floor class. Well, it actually, if you're going to do this systematically and professionally, it doesn't make a lot of sense. It does. Because like the more you put work into using your own structures and your data, then the less you depend on other things and the more reusable your code is for yourself. The only problem is that in particularly there's a small technical problem inside of Grasshopper, inside of a Grasshopper component. If you create a class inside of a Grasshopper component, then you cannot exactly just write the same class on a different C# component. You would have to be copy pasting that code in all the C# components, and even so, I'm not entirely sure that it will exist. If you write your own class in one component and you paste it on another, I'm not sure that even compatible. So the only thing that you need to do is you need to actually write those classes in an external file, a DLL library that becomes this library of your own code and your own classes and your own methods that you can then share amongst all the instances of C# components. In fact, if you do that, you're basically doing almost what Rhino Common does. Rhino Common is just this one file that is shared among all the C# script components and that gives all the components access to vectors, points, lines, nerves, etc., etc. So if you create your own geometry classes or floor plan classes or whatever, and you load them into your C# components, then you're good to go. So your objects get passed around as Grasshopper data types? Kind of, yes. But if you create your own classes in the C# components, then when they get passed around, they lose, because it's complicated to explain, but basically you can't really share the same class between Grasshopper components if you have created the class inside of the Grasshopper component. If you load it from an external file, then basically the reference to that class maintains the same, but otherwise they are different references to the same class. Arastio, a question about robotics. Could you explain a bit about singularities in robot arms and how you prevent them? What is considered a singularity? All right. Okay. Let me drink some water for that one. A singularity in a robot is an area where if the robot was to maintain constant linear speed across that area, then the motion of one of the joints or some of the joints, the angular velocity of each one of the joints would have to approach infinity in order to be able to maintain that linear motion. What does that mean? Let's say, imagine that my arm is the robotic arm, okay? And that I'm doing a linear motion that is going from this point to this point here, okay? So I'm doing this, and you can see that I'm moving the angles of my arm, my blah, blah, whatever, and each one of them is moving at a different angular rate so that I can maintain this linear speed here, okay? The problem is that there are certain areas around the robot where if in order to do that, some of the joints of the robot will have to speed up a lot. So for example, let me show you. You may want to do this with me. If you try to maintain that linear motion, but then that line is very, very close to your chest, okay? If you start moving like this, right? At some point when your finger is very close to the arm, you can see how your shoulder and your elbow have to rotate very fast to maintain that linear speed, okay? So that area around your shoulder would be a singularity because the robot would need to rotate very fast in order to maintain that linear speed. Singularities are bad because robots cannot approach infinite speed in their angular motion. So that's why when you are moving around an area that could reach into a singularity, the robot just stops automatically, okay? Because one of the joints accelerates too much. The ways to avoid that is that there are, in industrial robotic arms, for example, where these areas are is very well documented and known. So for example, in an industrial robotic arm, if you want to move on top of the base of the robot, that is a singularity area. The cylinder on top of the center of the base of the robot is a singularity area, because if you do this, you could see how I have to rotate my arm, like my shoulder, a lot to maintain. Another one is if your robot is like that and it has the wrist here, doing like this, all right, is also a singularity area, because if the moment where this joint here is aligned with this one here is a singularity area, because if I was going up, 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 I would have to rotate very fast to keep going up. And how do you avoid them? Well, with experience, knowing where they are and trying not to move the robot around them, I guess. You can also do some pre-computation, and then just if you know what motion you're going to follow, just do a check across all those targets for singularities before you actually go into them. And then if one of them is too close to a singularity, then you write a program that just chooses to avoid it somehow, you know? Also, you can use joint motion. If you use joint motion doesn't have singularity problems. But then joint motion has a whole other set of problems, because with joint motions, like sometimes you can't really predict where the robot goes, so you may start hitting objects and that kind of stuff. So it's not great, okay? Before you say goodbye, what is the main difference between the Grasshopper SDK and the Rhino Common API? The Rhino Common API, so the fact that one is called SDK and the other one is called API, it's pretty much the same. They're both just basically collections of methods and functions and classes that help you work with Rhino and with Grasshopper. The difference mainly is that Rhino Common has a large set of all the geometry classes that you want to use for vectors, nerves, etc., etc. And actually, Rhino Common is partially open source. So a lot of that is code that is written in C++ and that you can check online. The Grasshopper SDK is also a collection of data structures and methods, etc., etc., but it's a bit more specific to Grasshopper. So for example, it also has some data types. So Grasshopper has its own transformations and it has its own, some numbers, complex numbers, I believe, are also part of the Grasshopper. They're not part of, but anyway, it has its own implementations because some of those data types are specific about how Grasshopper works and how Grasshopper marshals, how Grasshopper changes types between objects. But also a lot of the collections that are in the Grasshopper SDK, they have to do with how actually Grasshopper works. So the fact that from the SDK in Grasshopper you can access things such as, for example, the color of the canvas, or like you can ask how many cables are in your definition, or you can change some components from active to deactive, etc. So you can start messing with the actual Grasshopper interface from that SDK, which is a lot of what, for example, what MetaHopper and what a lot of what the components in MetaHopper by Andrew Human, what they do. They actually use C# code to mess with the Grasshopper document and do changes and rearrange things and change colors, etc., etc. So the Grasshopper SDK is a bit more about messing with Grasshopper rather than using geometry objects, which is more part of what Rhino Common does. Okay. Rafael Company, the OArch forums, Blender Beam, and so on. And there's a kind of Grasshopper for Blender called Sverchuk. I've seen that, yes. I don't know anything about Blender, but it could make for a nice. I know, I saw that a while ago. I just haven't checked it out. And I'm also not a great Blender user. And I think also Blender is Python based. Like, ugh, you know? So, so yeah, maybe sometime in the future, but it's not on the list anytime very soon. Jose, can you try code on a robot object in Rhino? Actually, that's part of my plan. Whenever I have time to create a course or like a series on robots, the first thing we're doing is we're going to build a robotic arm geometrically and with rotations and that stuff. Is a really nice and funny exercise and fun exercise. So we will do it at some point in the future, yeah. Okay, I think with this, I'm good. Thank you very much, everyone, for sticking around so long, and I'll see you on the next live. I'm not going to live stream next weekend because it's my birthday, so I'm going to take it off. So I'll see you probably in a couple weeks or so. Okay, so thank you very much, and see you on the next one. Bye.